ability to pair with the X is again reduced. Now, why isn't the X rotting? The X isn't rotting because two X's can still recombine in female meiosis. So genes on the X remain healthy because of ongoing recombination on the female side, whereas the Y is rotting because it's only being passed through a clonal line of males. Let the tape roll. Oh, some more rotting. This is just, cover your eyes if you can't stand the sight of it. Right. It's very hard for somebody who works on the Y chromosome to actually see this because it could very well be continuing to this day. Okay, now we're going to pass the point where we part company with the kangaroo. And now something interesting is going to happen. Another autosome is going to contribute a fresh supply of genes to both the X and the Y. This kind of renews the game. Starts the game roll again. But look, the Y just did another inversion, even within some of this newly acquired autosomal DNA. So guess what's going to happen? More rotting fruits and veggies. This is still, I mean, it's probably not happening in too many of the men in the room right now, but XY recombination still continuing just out at the ends. I think we're going to be desperately in need of some new kind of theme here. Unfortunately, as we move now down into primate evolution, well, we're not quite there yet. More shrinking. Really a tough time. The whole last 300 million years have been quite tough. Now we're getting down into primate evolution. And some good stuff is going to happen, guys. It's okay. Now, this other autosome has a spermatogenesis gene. It's called DAZL. And this autosome is kindly going to contribute a copy of this spermatogenesis gene to the Y without asking the permission of the X chromosome. Let's let the tape roll. So we're going to see a copy. As the tape rolls, we'll see a copy of the DAZL gene insert into the Y, where it's now called DAZ. And an amazing thing happens. The gene gets duplicated on the Y chromosome, and then those two get duplicated again. So we end up with 4 copies of DAZ. It turns out the spermatogenesis genes on the Y, now fortunately none of this red stuff got lost, the spermatogenesis genes on the Y in many cases arose through this process of migration from autosomes. And so there we are. We got the sex-determining gene, SRY, one of these surviving housekeepers, RPS4Y, and spermatogenesis DAZ. That gives us the modern human X and Y chromosomes, of course, in the context of the genome.
So again, we kept talking about rotting fruit. If you don't have an homologous partner to recombine with, if mutations occur, they can't be replaced through the recombination. They're lost. And so that's contributed. So once the X and Y became no longer homologous, recombination was greatly diminished, and the Y began to lose sequences through deletions, through mutations that couldn't be replaced, and that continues probably to this day. Okay, but ultimately, originally X and Y were homologous autosomes. Okay? Back when gender was determined by temperature. Okay, and for some reptiles that still occurs. Yeah.
Well, that's because they just can't recombine again.
Well, but you can only recombination between homologs requires the sequence have to be very similar. If they're not similar, they can't pair up. They can't recombine. Okay. We'll see in what's coming in the modern gene therapy using an enzyme called CRISPR-Cas is, and this is already shown, they can do this already clinically, so this is starting to accelerate right now, is if you locate a mutated gene and you want to correct that, what you do is you import into the cell this enzyme that will cut out the gene, and it carries with it the correct sequence. And the sequence will insert it correctly because it will have ends that are homologous, that are similar in sequence, that bracket the target, and it just kind of pastes it right in. But it requires a similar sequence. So you can send in with a guide molecule the piece that has a sequence similar to the mutated version, and it'll be replaced through this recombination effort. But if they're not similar, they're not going to match up. Okay, and that's where gene therapy is headed with. this new tool called CRISPR-Cas. All right. This is something I'm going to cover this really fast here. We went through this in lecture. Talked about how some germ cells, sperm and egg, can have a wrong number of chromosomes. That's called aneuploidy. And it's a result of an error in meiosis, what's called non-disjunction. And it can occur either during the first meiotic division, as shown on the slide here, or it can occur in meiosis 2, which is coming up here. If it occurs in meiosis 1, again, what happens is that we see that normally the homologs should segregate at meiosis 1, but here we see that in one case here, only one set of homologs correctly segregated, the other two didn't. We end up with every daughter cell with the wrong number of chromosomes, aneuploidy, okay? Polyploid and missing. So all of these, if they're fertilized, are going to probably lead to a spontaneous abortion, miscarriage by the female. Okay. And this can also happen in meiosis 2. And at least in that case, 50% of the gametes will be normal. Because in meiosis 2, remember this mitotic-like separation, where we're separating sister chromatids. And again, these are mechanical processes that require intact structures to function correctly. And anytime there's trauma or a machine that's not correctly manufactured, this can lead to these sort of errors. Okay. And I believe most people think that most miscarriages are due to non-disjunction, so they're not rare. They are not rare events. Okay. All right. One of the few aneuploidy that leads to a survival at birth is Down syndrome, trisomy 21, and it's almost always non-disjunction that occurs in the female. And you can see from this graph here, if you look at the incidence of Down syndrome per 1,000 births, relative to mother's age, that there's a sharp increase when a mother reaches her mid-30s. Okay, and again, I made the point that that the eggs you're carrying in your ovary are actually older than your birth date. So, as you live through a dangerous world, and also it might be a genetic component. I don't know about that, but if you have a maybe a lifestyle that's not conducive to maintaining your health, maybe this might accelerate that process. I'm not sure about that. All right. Aneuploidy can lead to abnormal combination of sex chromosomes, where if the egg has no X chromosome, fertilized by a Y, well, there's no living offspring here. If a sperm fertilizes an egg without an X, if it carries X chromosome, you have Turner syndrome, a sterile female. Sometimes you can have the multiple X's and Y Klinefelter. So these are, again, males with female body shapes and poorly developed breasts, but they're sterile. Then you have these triple X super females. We'll talk about that in labs. I'm going to skip through that as well. If a woman's family has a history of genetic issues, or she's starting reproduction relatively late in life, she may be recommended to undergo what's called amniocentesis. We're at around 12 weeks. So this is early in the fetal period. So the first eight weeks of a fertilized egg is called the embryonic period. That's when most of the organs are set down. From week 9 onward to full conception of 40 weeks, that's what we call that offspring of fetus. And essentially, all the organs are set in place. Now it's just growth and development of brain tissue. The last organ to form, of course, mature the lungs for the obvious reasons. So they'll take, so the baby, of course, in a primate is in this fluid-filled sac, the amniotic cavity. The fluid is the amniotic fluid. This is when this membrane breaks right at the beginning of labor. That's when you break your water. They'll insert a needle and collect amniotic fluid. And there's always floating in the amniotic fluid a number of fetal cells that are then recovered and cultured. And then they use a plant toxin like colchicine to stop mitosis at metaphase, and they can harvest the metaphase chromosomes and do a karyotype. They can also perform biochemical tests on the fluid to look for certain biochemical markers of genetic disease. Okay, if you are desperate for an offspring, but you're having trouble conceiving with your partner, families will often resort to in vitro fertilization, a test tube baby, at great expense, usually not covered by insurance. There's a lot of institutions that perform this for desperate couples. They charge a heck of a lot of money, what I understand. So they want to give if you're going to shell out $20,000-$30,000 to have a kid through in vitro fertilization, you'd like some sort of a guarantee you're going to get a good kid. So what they'll do is they'll often they'll harvest the eggs and sperm and then fertilize them in the lab and then reimplant usually a number of early stage embryos in the female because not all of them will implant successfully to trigger a pregnancy. So that's why often women that undergo this procedure have multiple births. And usually before they do that, what they usually do is they implant at the 8-cell stage after 3 divisions post-fertilization. And what they'll usually do is they'll do a pre-implantation diagnosis. They'll harvest 1 cell, leaving 7 behind, to do a chemical genetic test to make sure that that your customers are satisfied. And so far, leaving 7 cells remaining doesn't appear to disrupt the normal development of the individual, since this has been done for nearly 50 years. All right, I'm going to leave that behind now and complete chapter. Actually, this is not so much chapter 13. A little bit I'm going to add here. If you want to, something I'm a little bit interested in, and have done a little work at the Newark Center, is tracking ancestry through gene markers. Sort of what you now see advertised, like for 23andMe. People think, oh, if I do this 23andMe and spend a couple $100, I get all this genetic information. I'm 20% this, 20% that, and they think it defines them. I think it's kind of bullshit. I mean, you can kind of learn about maybe where some of your history's from, but you know, you hear about people, well, I thought I was German, I listened to polka music and drank beer, and now I find out if I'm Russian, so I don't know what to do. So, I mean, you are who you want to be in a way. So we're all mosaics in terms of, no, there's no such thing as a pure race anymore in the world, no matter what Adolf used to think, or Breitbart. But you can track ancestry